Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we will continue Chapter 1, reviewing last semester's material starting at Chapter 7. So if we look at ADA1, in our first half of our video, we covered through analysis of variance and non-parametric methods. In this video, we'll cover Chapter 7 through the end, which is categorical data analysis, regression, and so on. So here's the course website. I'll scroll on down to our course notes, and we are doing the review here. Okay, so here's Chapter 1, and I'm going to scroll on down after analysis of variance to when we start Chapter 7 for categorical data analysis. So in Chapter 7, we covered categorical data analysis, that is, estimating proportions, so probability of success and failure within a population. We have an example here returning to the Turkey data set where we can do cross-tabulation. So we've got origin, which has two categories, Virginia and Wisconsin. We have whether or not turkeys are greater than 25 months, and that's this variable, which is either false or true. They're ordered in this direction both because it's alphabetical and because the numerical value of false is 0 and true is 1. So it's sorted in that order. And we see that for the Virginia, we see there are 6 to 2, so about 3/4 for Virginia that are old, whereas Wisconsin it's about 50-50. We can do chi-square tests of association, and in this case we have small sample size, and so we have a warning here that the approximation may be incorrect because we have a very small sample size. It gives us the chi-square value and the p-value for that comparison. And we can either perform Yates continuity correction. This false means that it did not, or we can. The default is that it does perform the continuity correction. And in these small samples, it actually can make a big difference. And Fisher has an exact test for a null hypothesis of no association. And in many cases, I would prefer this test statistic. We have ways of plotting categorical data. A mosaic plot is the one that I've been showing you from the VCD, so Visualizing Categorical Data package. And here we have origin on the vertical axis, greater than 25 months on the sorry, I said that wrong. Origin on the vertical axis, greater than 25 months on the horizontal axis, and the area is proportional to the number of observations. So here, Virginia had 2 false, and 6 true, whereas Wisconsin had 3 false and 4 true. And if there was no association between origin and age, then we would expect these all these rows to have the same distributions and the columns to have the same distribution. So basically the lines that separate the rows and columns should line up like a table. And this offset suggests that there's a little bit of a difference, but we have very small sample size, and this is not a very big difference. So on the right we have created some artificial colors for these small differences. In fact, there are colors in this first plot which, if there were big differences, if we had either very big differences or we had a very large sample size so we could detect a small difference, we would get colors for these cells that indicate which cells contribute to the chi-square statistic, which gives us a way to interpret these categorical tables by showing us which categories are different than you would expect. All right, so So that's something you should be familiar with, doing chi-square tests and plotting data. We also in class calculated the differences between observed and expected frequencies in tables. In this case, the statistic over here, what we observed was red, and what we expect is blue. And so if these blue and red bars are basically the same, then we are consistent with the null hypothesis of no association. The differences here are summarized best using the contribution to the chi-square statistic, which is, I probably do not have, I'm paging up now, the equation that gives you this. I'm going to page back down to that plot. But these are, remember, a chi-square statistic is the sum of these squared residuals. And we've got what we observed, so the red bar, minus what we expected, and we square that difference in the numerator, and then we divide that by what we expected in the denominator. And if we do that for each of the 4 categories, this vertical bar, the gray one on the right-hand side, is that contribution of chi-square. If you add up these 4 bars, that is the chi-square statistic. So I plot them in descending order so that the one on the left is the main troublemaker in terms of rejecting the null hypothesis, to focus our attention on those differences. In this case, we don't have enough evidence really to say that there's any difference here. In Chapter 8, we looked at the relationship between 2 continuous variables. Correlation is the measure of how linearly associated 2 variables are. And in here we're looking at rocket propellant data. So we read that data set in and we plot it. This is the age in weeks that the rocket propellant, so the rocket propellant in this example, let me page up again really quickly, has 2 types of propellant. And those 2 types of propellant are bonded together. And so when you light this rocket propellant, it burns off one type of propellant for the first liftoff part, for example, and then for the sustaining burn, once the rocket's in air, it burns the second type of propellant. And what we're interested in is that this bond between the propellants is strong. And so the shear strength is how strong they're bonded together if you try to separate them, not by pulling them directly apart, but by shearing them, so sort of pushing one to the left and one to the right. If you had if your rocket propellants were bonded vertically, right, from the tabletop up to the ceiling, if you pushed one to the left and one to the right, you're pushing against that horizontal bond. And so that's the strength of the bond. And what we see here on the vertical axis is the shear strength in the pounds per square inch, that the older the propellant is, the weaker the shear, or the less pounds per square inch it takes to break, so the weaker the bond. And so maybe you want to make sure you launch your rockets, 6 months after you, or maybe even less than that, after you make that propellant. So we're looking at regression and correlation. The correlation is the linear association between these 2 variables. We want to take care about observations that seem unusual, observations 5 and 6 in this case. And notice I've plotted the ID number of each observation so that we can go back to the table, and if this was my data and I collected it myself, I would probably have some notes about how each observation was collected, and I could go back and say, hey, what happened on observation 5? It seems that I measured this 6 weeks in, roughly, and its shear strength was much less than what we expected it to be. Same thing for observation 6. So maybe someone else was working that day. Maybe it was unusually humid in the shop. Who knows? But often you want to find some meaningful explanation for an unusual observation, if you can. Or maybe that's simply natural variability. However, it does seem that the rest of these are pretty consistent along this straight line. So you want to think hard about your data, not just fit a linear model, interpret the beta coefficients, look at the p-values. No shortcuts. We want to understand the whole story of our data. So here is our linear model. So you want to be able to interpret the coefficients of your regression model, know where this t-statistic comes from, interpret the p-value, interpret the r-squared statistic as the proportion of variation that the model explains over and above the grand mean of the response variable. What does this p-value do? What test is associated with that? I'll give you a hint. It's the same as this one in this case. Basically want to know about all those observations, or all these numbers. What is this degrees of freedom? The residuals degrees of freedom? Okay. Even what does the standard error estimate? Okay, that's the standard error of the residuals, meaning that's the standard error of the variability of the points vertically about the regression line. Okay, so all those things should be very familiar to you. In regression, we always plot diagnostics. In fact, probably want to look at residual plots before you even start looking at the linear model fit results in those p-values, because the p-values aren't very meaningful unless these plots are consistent with model assumptions. So we want to look at this residual plot here. We've got our fitted values, which are basically the y. This is the regression line. These fitted values, that's the y value, or for each observation, and here's the residuals. Okay, against fitted values, and we should see basically a horizontal line. What we do see, at least my eye catches, this value number 6, which is down here. I can make this bigger. Okay, seems to be unusual, and 5 seems to be unusual. The rest of them seem not too bad. Okay, your eye might capture this pattern of sort of this parabola, this downward curve, and that may in fact be fairly meaningful. There's 7 points in the center which are all greater than 0. So perhaps a straight line is not the best fit for this data. Maybe we want to fit a curve, a quadratic parabola, right, to this data. We want to make sure you know how to interpret Cook's distance as how much does the regression line change if you remove one observation. Okay, if you remove observation 5, let's scroll up and take a look at that. I'm going to page up to that plot. Oops. Okay. If I remove observation 5, what happens to the regression line? Well, observation 5 has some leverage, meaning it pulls the regression line down on this side. Okay? So if I remove observation 5, this regression line is probably going to move upwards. And it's going to fit, it's probably going to pass through maybe between 8 and 19 up here. It's going to pass through these data a little bit better. Okay? Same thing with 6. 6 pulls this regression line down on this side. In fact, maybe the thing to do is remove both observations 5 and 6. Then this whole regression line moves up and fits all these data in the middle really nicely. So Cook's distance tells us how much the regression line would change if we remove one observation and only one observation. Okay? So 5 is influential by itself. 6 is also influential by itself. 19, a little bit less so. But really, if you remove 5 and 6 together, and that Cook's distance does not look at pairs of points, that may end up being the best choice. This vertical axis here, Cook's distance, is the same values on the left. So for example, observation 19, which is right here, is the same height in this plot, observation 19, okay? Along the horizontal axis, I will do my best to get better at navigating with Adobe Acrobat in these notes, is leverage. So remember what leverage is. Leverage is how much an observation is an outlier or an extreme point in the x direction. Okay, so along the x-axis, we'll have low leverage if you're near the mean of the data, so on the left-hand side of this axis. And then as you become an extreme observation, to the right here, you will have more and more leverage, meaning more influence in pulling that regression line towards you. Leverage is possible influence, or it's sort of you should be concerned when you have a high leverage point that the point could easily influence the outcome. It doesn't need to be influential, but it very easily could. Cook's distance, on the other hand, is how much influence the point actually had. So if you have points in the upper right-hand corner, that's suggesting that the point is influential along Cook's distance because it had high leverage along the leverage axis. In this case, we have points 5 and 6, which have moderate leverage, but are influential just the same. Observation 19 has, for sort of fairly weak influence, but it's because it is an extreme point in terms of leverage. So if we scroll back up to our plot, we see observation 19 in the left-hand corner here. It's the most extreme point toward the left. The point that probably has the second biggest influence, leverage, not necessarily influence. Leverage is probably 13 because it's the most extreme observation to the right. All right. So all those ideas should be familiar to you. Let me scroll back down. Here is the residuals on the y-axis versus the age in weeks. That's the x variable. And notice it has basically the same shape as the plot above with the fitted values. However, the fitted values are basically the y-axis for the regression line. We had a negative slope. So this point number 5 in this bottom left-hand corner has a high fitted value, around 2400. Let me scroll up to that, observation 5. Observation 5 had a high fitted value, about 2400. So observation 5 is predicted on the blue, it's this blue point on the regression line right above observation 5. So that's, and because this has a decreasing relationship with relative to age weeks, I'll jump back down. You'll see that this plot of fitted values is flipped left and right versus this plot against age weeks, meaning that this triplet of points on the right-hand side for age weeks is this triplet for the fitted values. We had high age weeks for these 3 points and had a predicted low values for the fitted values. So those have flipped axes when we have a negative relationship. All right. QQ plot tells us about whether the residuals are roughly normal or not. 5 and 6 seems to be outside these bands. They're a little bit more extreme than we would expect a normal distribution to be. There's also a little bit of curvature here, which suggests skewness in the residuals. And this last plot is versus the order of the data, so just observations 1 through 20. This plot is only really meaningful when the data is in the order it was collected, and we want to check to see whether there's dependence between one observation and consecutive observations. You know, if you show up one day and you make a bunch of rocket propellant and you have a bad day and you see that there's a bunch of residuals that are all the same and they're all right next to each other. Notice, for example, observations 5 and 6 are right next to each other. That maybe there was a bad day, right? They mixed the propellant bonding material and they didn't get the ratios right. And maybe that explains these two. You know, maybe Hank did it and Hank did a bad job. All right. So that gives us a meaningful reason to exclude these two observations as being systematically different from the rest, so that the relationship is not influenced by some weird situation. All right, you want to be able to interpret the slope. You want to be able to write out what the regression equation is. All right, I redo the analysis excluding observations 5 and 6. Notice that I use subsetting to do that. So here the negative or the minus sign here indicates I'm going to exclude those observations, rows 5 and 6, and I'm creating a new data frame, rocket 5, 6, which actually excludes those, and you can see between rows 4 and 7, those row labels, 5 and 6 isn't there anymore. Okay, so I go ahead and plot and fit the data, and looks pretty good. You can see that little bit of curvature perhaps. Maybe a quadratic model would be slightly better. And of course, statisticians often start with a very simple model because we admit to not being experts in things. And so it's possible that a better fit, if we knew more about how bond strength depends on time, if we actually had a physical chemical model for that, we would probably use that model and estimate the parameters within that model. Okay, but this is a simple first step that a statistician might take without knowing much going into it. Look at the residuals, everything looks pretty good there. All right, there's some summaries for that. Things. Okay, so we also last semester covered the basics of logistic regression. For example, the Challenger O-ring example is that whether O-rings fail depending on temperature. But that's what you need to know going into this semester. Maybe the last thing that you want to be comfortable with is using Markdown. So I do have videos on using Markdown. Just as a very quick 45-second example, if you open a new script with RMarkdown, you can create a title here for an example, your name and the type of output. We're going to be using mostly HTML in this class. Here is a Markdown file, and I can maximize this window. This is the entire file. There's 23 lines. The first several lines is called the YAML, which stands for Yet Another Markup Language, YAML. Okay, and not that that's important, but I'm defining what the title is, who the author is, the date, and what sort of output it is. We'll see other options to include up here in examples in class. And notice it has a few things going on. I've got text here, and then I have these triple backticks with R in curly braces, and then R code. And when I compile this, and in this case compilation is done by knitting, so I'm going to click knit, and it will require me to save this file first, so I'll just call this example. And .rmd is RMarkdown, and here's the output for this file. It's got the title. In fact, let me scroll this over a little bit over here so we can see both some of the document and the output. So we've got the title, we've got the author, we have the date, and in fact this is an HTML document. All this text right here shows up as text. We have links that we can click on. We have bold, and we probably have italics somewhere. It's easy to make italics as well. And then here's the R code, summary cars, and then the output for that. Oops, the output for that. So what's beautiful about this is it gives you an environment for reproducible research, meaning that if you give someone this Markdown file, they can see all the decisions you made, whether you excluded observations, how you plotted things, all sorts of things. All the decisions that could be hidden if you were using Microsoft Excel, for example, and we're clicking around in Excel. So plots show up nicely in here as well. Okay, so really nice environment for producing documents, and this is what you will have to use in this class, and I believe you will find that you will love it. And I will typically give you a starting point document to add to or edit after that. All right, so that is your review for this class. Next video, Chapter 2.